part 3 and 4. Part 3 really was just like you taking down a couple of notes. It wasn't too much, but it's an intro for what we're talking about today. And then part 4 was review of how thermochem relates to like thermodynamics is going to be then related to electrochemistry. But our electrochem test is electrochem and a review of thermochem. That's why I'm hitting thermochem a little bit more right now, especially since our midterm is January the 12th. Okay, but these are important dates. You got it? Like 4 or 5 of you turned in your equilibrium test corrections already. Thank you. Otherwise, just the rest of you guys, I'll be here tomorrow after school if you want to hang, but I have a meeting after school on Thursday. Electrochem test is next Tuesday. Okay. All right, so make sure that gets in the box, and then have your holiday review on your desk. Because we're a little short on time, I'm going to be running around kind of during notes, so have that there for you. We are going to take notes. There are a couple of things in the packet I provided you, the first day of the student. So if you want to pull that out now, that might be beneficial. And then let's roll. And I just had to go outside, so I'm still like warming up. Ooh, my clothes are cold. All right, so review. You guys are rustling on paper still. What is Gibbs free energy's definition? Gibbs free energy. Energy available to do work. Thank you. Energy available to do work. So there has to be a relationship between energy and work, and we know there is a relationship between them. First of all, they're the same unit. It's joules, because that's how work is established. But delta G, which is Gibbs free energy, has a relationship to work. So I'm trying to just I'm taking two big ideas. I'm trying to start to show you the formula or the relationship between them mathematically. That mathematical relationship is something that you did read about on part 3 of the simulation. So from electrochemistry perspective, we talk about kind of energy, not in the sense of joules, but we talk about energy in the sense of cell potential. Cell potential is the difference in the anode and the cathode's ability to give up electrons or to take electrons. So that right there, where do we get information about cell potential? We do that. We look at the chart, but what are you telling me? You're looking at the reduction potential, right? So this is E cell. E cell is E of the reduction, the cathode, minus E of the anode, which is the oxidation side of things. There's knots on all those. Okay, so cell potential, which is our differences in the reduction potentials of two different sides of a battery, is related to work, but it has opposite signs with reference to like the perspective of that electrochemistry or that electrochemical cell. So when you're producing energy, we think that is positive volts, making energy. But then we capture the energy at the top. We can measure the energy at the top of the cell with the voltmeter, but then we can siphon that energy off as electrons, which is electricity, and we use it to do work. So essentially, though, the battery itself is making energy, so it's got positive voltage, but then we siphon it off, so therefore it loses energy to its surroundings, which is why we call it negative work. So that's why they have opposite signs. And then cell potential is in volts and work is in joules. That's kind of what I just said. I'm going to get down here in a second. So all of these things, whichever sign it is we're talking about with the different perspectives, it's all galvanic, which is thermodynamically favorable. Whew. So our positive E cell is related to negative work, which is a thermodynamically favorable process, which is going to have a negative G, and that work is being siphoned off, so it's done on the surroundings, which means that the system lost it, which is why it's negative. So this is a lot of just correlating positives and negatives to different variables. Are you kind of piecing these things together a little bit? What you should realize is that positives and negatives, and understanding like what that positive and negative is referring to, is really important. All the different variables will become related to each other mathematically. And so voltage, we know, is positive. Okay, there is a relationship between volts, joules, and coulombs. Those are 3 different units. They all kind of relate to energy, right? Work is definitely in joules, which is definitely like the purest unit of energy we have. volts is related energy, and coulombs, which is the charge that electrons carry, is related energy. So these have to all be related to each other, and you should know that relationship. Does anybody have their reference table available? Because I believe it says it, not the honors chem one, your reference table. Well, if you look on the bottom right hand side, it says 1 volt. Do you guys see that? Bottom right hand side. It says 1 volt is equal to 1 joule per coulomb, right? It doesn't say 1, but it's 1 coulomb. So this is the relationship. So you don't have to memorize it. You just have to appreciate that there is a relationship, and you can find out in your reference table as needed. So that relationship is actually this setup. E cell, which is volts, is equivalent to negative work, which is in joules, per coulomb, or per charge, per a number of electrons or charge that those electrons carry. So Q is called charge. Q is not heat. Okay? In electrochemistry, Q is charge, which is related to the unit coulomb. But if you know the relationship here, you could finagle different pieces and tell me, like, you know, how many volts were made given this amount of energy and this amount of coulombs. So there is a negative relationship, though, between, or indirect relationship between the E cell and work. So this blue right here is actually the expanded definition of what this is. So read that just so you can, you know, speak it if you had to. Just to make sure I started videoing. Just make sure. Okay. So after recognizing the relationships between joules, volts, and coulombs, you can take this and then, including, I'm just actually excluding all these units I had written out first. I rearrange the equation, E cell is equal to negative work over Q, to be negative work is equal to E cell times Q. Q again is what? Charge, right, which is established in coulombs, not heat here. I know there's so many letters we could use, but they decided to use Q again. Okay, so Q, which on your reference table is written out, so like you can't mess that up. It's right like 2 lines above the volt thing we just looked at. It says Q is charge in coulombs, and charge is related to charge of electrons. So you have to look at all the electrons in the 2 half reactions that make up this overall equation, and those electrons carry a certain number or a certain charge. But we have to look at the number of electrons. So there is a number, an N, that's coming into play as well. So this is just defining what Q is, and then there's a little bit more to this. Q is actually equal to NF. So N times F. N, we always establish N in the same way in every different theme in chemistry. What is N? Moles. And in this case, since we're dealing with electrons moving, this is moles of electrons. Okay, so N is moles of electrons. And F, which if you still have your reference table out, do you see that in the same place we were just looking? There it is, constant, right? 96,485 coulombs per mole of electron. It's a big number. We try to round it where we can if we're estimating. So Q is equal to N times F, where N is just how many electrons are transferred, and F is what's the charge per mole of electron. So it gives us an overall total charge transferred. If we had 5 moles of electrons transferred, it would be 5 times the charge. If there was only 1 mole of electrons transferred, it would be that charge exactly. So if you have more electrons, you're making more volts, right? Right? So you should be having a higher charge because you've had a higher amount of energy or difference in electrochemical potential. So if Q is equal to N times F, on your reference table it says I is equal to, I'm going to wait on the time. All right, so we have a relationship between work in E cell and Gibbs free energy. And then that work in E cell has a relation, the piece that connects it is charge, and charge has its own equation, which is N times F. So we're going to try to put N times F in where Q is, because it's one and the same, right? So I'm just going to put N times F in where Q is. And that gives us E cell times NF equals negative W. You with me so far? We're just rearranging equations. I'll get right back to this. I pre-wrote some things so that I could use my time wisely today. So what did I do here between this line and this line? Right, just switch the negative to the other side. So essentially negative NFE, negative NFE, which is E cell, is equal to work. Well, work has a relationship to what other variable that we started off with? Delta G, or which is joules, which has a kilojoule or joule relationship. So this right here, delta G is equal to negative NFE cell, is what I have here. Not there, but they're here. Now, is that one on your reference table? Pretty sure it is. Yes. So I know you can use a formula. I know you know what these variables mean. You could easily find it because they're defined as a variable on the side of your reference table. But you should just like be able to think of how the variables are related, which is why I like to walk through this sometimes. So the equation that you should know is negative, or delta G is equal to NFE, negative NFE, which is written this just in a different way here. N stands for moles of electrons. We got to be specific in this case, right? F is, and E cell is volts, which is the difference in reduction potential between anode and cathode. Okay, so this means that, like just like in the lab we did before we left on Thursday or Wednesday, we just put the two electrodes to two different metals, and what do we measure? We measured E cell, right? We measured volts. So we experimentally now can take an experimental piece of data, which is E cell. We can look at the equation and find the number of moles related, and then we can calculate from experimental data delta G. We have never, ever, ever been able to do that before. Yay! This is supposed to say yay. Yay. We've never been able to experimentally take data and find delta G before. This is awesome. This is our new equation that can do that. Everything else has been, use a table and do delta G products minus delta G reactants and just get your theoretical delta G value, right? Or H products minus H, or delta H minus T delta S gives you delta G. Everything that's been theoretical, theoretical, theoretical. This is actually experimental. It's an interesting thought. Okay, I'm glad you appreciate that. So, what units should delta G be? What should it be? Joules or kilojoules. Okay. What units is in? Okay, so I'm going to kind of write this here. It's right here, but I'm trying to hide it. Moles of electrons, right? What's F? So 96,485 coulombs per mole of electrons. Okay, what's E cell? Volts. Okay. So what happens whenever you go through here and cancel units? So moles of electrons cancel, and you end up with Coulomb volts. Well, a Coulomb volt is a joule, because a Coulomb volt, we established earlier, coulombs times volt gives you joule. Like, that's the relationship. So if you ever end up with Coulomb volts and it says to define the answer in joules or kilojoules, you need another relationship. So a Coulomb volt is equal to a joule, which you could convert to kilojoules if needed. We good? All right, so this is most of like the background for everything today. I'll repeat myself a couple more times here, but we're going to try to do some examples. Okay? Give me a thumbs up when you're good to move. The units are pretty, well, they're always important, but they're important to make sure that you're canceling, showing the right units so you can find charge or find work. We got that. So this is repetitive. This is like another way I used to explain it, but I kind of like what I just did, so I'm going to stick with that. So this is just, we're going to go with that. This is just showing you that work times charge and energy, or volts, and then the charge is equal to N times F. Those come together to make work is equal to negative NFE, which we just said work was what? Related to delta G in an indirect fashion, so that's why we keep it as, well, actually no, direct fashion, because I've already accounted for the negative. So that's just delta G is equal to negative NFE. Okay? So what I really wanted to ask of you was, we have to relate these quantitatively and qualitatively. So if you have a positive E cell, that means you have what kind of cell? What type of electrochemical cell? Galvanic or electrolytic? Galvanic, okay. If it's galvanic, delta G has to be negative. Or if you get a positive E cell, then you already know the delta G is negative because they have a relationship. Is this direct or indirect between delta G and E? Say again?
Direct.
No, I thought you said indirect. This negative right here makes an indirect relationship. As E cell is positive, delta G with this positive number is correlated to be negative. So that's why it's an indirect relationship. So as E cell gets bigger, delta G gets more negative, which is more thermodynamically favorable. So as E cell goes up, delta G gets more negative. So we make the higher we make E cell, the more spontaneous we make the overall battery, or the more thermodynamically favorable we make that battery. And then opposite, if you have a negative E cell, it's not galvanic, it's going to be electrolytic. And that delta G can be positive, which would be not thermodynamically favorable. I'm just trying to use both words, spontaneous and TDF, so that you still understand those are the same things. And then tell me one more thing. How does K, equilibrium constant K, play into this? So for this first statement up here, what is K? Greater than 1. Good, because products are favored. It's thermodynamically favorable in the forward direction. We want to make products. And then down here, K is less than 1, because we're still favoring reactants, not products. So everything's starting to find a relationship with another concept that we've discussed, and that's going to keep happening again for a month. So tell me when I'm good to go. Okay, majority. All right, so please do not write all this. The highlighted parts are really what I wanted to emphasize to you. This is just a side note. We talk about this amount of energy, this work being produced, but we don't really anticipate that what we calculate is not 100% always going to happen. When we have these electrons moving through this external wire, electrons have resistance going through the wire, because you guys know resistance, and you guys know there's a relationship between resistance, current, and physics people. Resistance, current, and amps? Yeah, right? VIR, voltage, current, and resistance. So anyway, there's resistance there, which means that the work's not going to be 100%. So we think there's maximum work, but we never actually get that maximum work because of the resistance or the friction that's occurring in the external wire. That's it. We will never meet our maximum work. We always calculate maximum work, but we'll never meet it. Got it? So say what I just said in layman's terms. Queen? Resistance of the flow. Good. Flow of electrons. That's really what that is. But in the background, the chemistry behind that is, as we lose some of that heat energy to friction, or just some of the energy to friction, it's actually satisfying that second law of thermodynamics, which is that as your process occurs, it's going to increase entropy for it to be thermodynamically favorable. So as it does that, the energy gets dispersed in different areas, which is why entropy is actually increasing. And then I already said all this. This is the third time I've said this. I'm going to just hit this. Moving on. Resistance decreases work. Okay, so here's the first example of many that's going to make sure you can connect all these pieces together. First, I know you see delta G is what it's asking for. You see the cell notation, what do you already know about cell notation? We know who's the wet and the wet, and cathode, okay? And I have to tell you these, I'll tell you these reduction potentials just so you don't have to look them up on your paper. But talk to the person next to you about these couple of things here, okay? Go. What can you interpret? All right, come back to me, come back to me. What does the not mean right here? What are standard conditions? All right, 25 degrees Celsius, 1 molar solutions if they were aqueous, and 1 atmosphere. Okay, what's galvanic mean or indicate? Thermodynamically favorable. And make sure you're also thinking, if you don't always write it, like thermodynamically favorable in the forward direction. What else does it mean? E cell will be positive. Delta G should be, and K is greater than 1. Okay, so if you are already told this is a galvanic cell, and I'm telling you right now this is a galvanic cell, so you can kind of predict what you're looking for. You can check your work at the end, which makes it nice because you have that confidence. According to how this is written, who's oxidized? So zinc is going from zinc 2 to zinc solid, or zinc solid to zinc 2? Make a choice. Solid, which has a 0 oxidation state, to zinc 2 plus and 2 electrons. Okay, who must be reduced? Copper what? 2 electrons yields. Okay, so we have our 2 half reactions, right? And this actually is kind of nice because there's no coefficient differences because we have 2 electrons lost, 2 electrons gained, we're done. So this is happening, this process is happening where? On the battery, which side, which area of the battery? The anode. And this is happening in the cathode. Okay, so far so good. You remember some stuff. Good job. According to, like, you know, we're thinking about what we're going to do. We're going to calculate delta G. What equation comes to mind for calculating delta G? Delta G, negative N F E. Okay, so to get in, we have to find what? Okay, so looking at total moles of electrons transferred, if I added up these equations, like stacked my 2 half reactions and added it up, what would my overall equation be? Zn. So I'm adding this and the 2 electrons, okay? But those 2 electrons cancel with those 2 electrons, so I'm excluding them for now. Yields Zn2 plus and copper solid. Okay, so there's no coefficient differences because the 2 electrons can't cancel. So overall, what's my N? What's my number of electrons transferred? Our number of moles? 2 moles of electrons, right? Because I have 2 moles of electrons transferred here, and they're given here, and there's no differences in coefficients or number of electrons, so I don't have to balance them out. If I did have to balance them out, the number would go up. Like if it were 2 and 3, what would be my least common multiple? 6, and 6 would be my moles of electrons transferred. Okay, and then how do I get F? Fairness constant, and how do I get E? So E cell is equal to E. I heard the cathode, which is another way, I'll write it like in my answer keys. E cathode, which is the reduced one. E anode, which is the oxidized one. All right, so let me tell you those values just so you're not looking them up. The zinc is, the reduction potential is negative 0.76 volts, and the cathode reduction potential is 0.34 volts. Go, find delta G. Negative 0.76 and positive 0.34. Once you find delta G, find the equilibrium constant value. Double check your sign. Do you know if this should be positive or negative?
I don't know that. Then I turned it on. I was just asking.
It's going to be an energy version, right? She's saying R, but is it 267? Yeah. All right, what equation comes to mind for K, finding K? Negative rat length, negative RT, okay. Okay, so you have, we have a large number. This is not the correct sig figs right now, so hold on. Negative, good. It's a galvanic cell, positive E cell, this is a negative delta G. Those correlations are good. And then I need, note that this is not a sig fig. The 2 moles of electrons are not a sig fig. It's a, you're counting, you're not measuring. Sig figs come from measurements being somewhat questionable. So the measured piece here is not the moles of electron, not the constant. A constant's a constant. And that measurement's coming from the voltage found, which is from the differences in electric, or in the reduction potential. So we have 3 sig figs here, so this should be what? -2. Good job, guys. Okay. So -212 or 212,000 joules. Now this normally is in kilojoules per mole or kilojoules, but I knew this next equation is going to be using what? Joules, which is why I never changed it. So what's the R value here? 8.314 joules per mole K. Kelvin. Okay, so you're thinking joules and joules, moles and Kelvin. So what's my T? How do you know it's 298? Because it has the knot. Good. So 298 Kelvin is 25 degrees Celsius plus 273, and then L and a K. All right, so this value for G is equal to blah, blah, blah. I need to isolate L and a K. So when I take 212,000 divided by, negative 212,000 divided by -2, or negative whatever this is together, then you'll get L and a K. What is L and a K? I actually didn't write that down. What is it? 85.7? Can I get a consensus? It's 85.7. And then now we already know K. What are K's units? Non-existent, right? So we're good. We know that these units are going to cancel. Kelvin cancels. Joules per mole is related to technically joules per mole. So the K is going to have no units. So then how do you offset LM? E. And that gives us K to be what? 6.2, I think. Give me 3 sig figs. 6.6. Well, I'm going to say 1.6 something because we need some sig figs. 6.2, okay. Times 10 to the 37. And we know it should be what? Just galvanic. greater than 1. Is that greater than 1?
Yes.
Heck yeah, all right, so we're good. So that should be your little pat on the back. Question?
So do you want to like use delta G minus divided by 1?
Oh, if you got those calculator skills and you want to plug it all in versus solving, baby stuffing it, you can do that. If you mess up, I can't give much credit because, you know, one-stop shop, you tend to maybe have a mistaken calculation. But if you set it up and then just do a quick, you know, it doesn't take that long to just quickly divide and then E, it's not going to hurt you. So overall, we know the relationship between G, E, K, yeah, work. Okay, so I could draw this right now, but I'm gonna hold off. I have a couple more things I'll talk to you guys about. That was pre-solved, so we could do that, but here we go. Sometimes you'll have an image, and it'll ask you about, like, how could you stop the flow of electrons, or it would talk about a switch in the system. It's literally just your galvanic cell set up, your external circuit, and then the switch will either open or close. So if it's closed, and the switch is connected, it's connecting the electrons so they can flow through the wire. That's called a closed circuit. Yeah? If it's open, it's called a open circuit. Open circuits, do the electrons flow? No, because there's an open spot here, so there's no more electrons that can flow. So then what would your E cell read? It would read 0 because it's not detecting the electrons flowing. That's just a side note. It's been like 1 or 2 FRQs in the past, so just want to make sure you know that switches can't exist. Switches are closed to allow for flow of electrons. That's kind of obvious, though. We good? Okay. And then I'm going to show you Nernst equation. Yes, I have to talk about this first. Okay. So the Nernst equation, which is a derived equation that's relating the E cell that we calculate from just standard conditions, it's relating that standard set of E cells to non-standard condition E cells. So what are some ways that we could not make something non-standard? Changing temperature, changing concentrations, changing atmospheric pressure. Many times we're talking about cells that are happening in aqueous solution, so many times we're going to change the concentration, and that's going to totally destroy what we thought our E cell was going to be. If I have a really big difference in concentration, the E cell could still be like generally close to what we thought, but I've changed then E cell because I've changed the conditions that are present. So that's what this is going to get us to, okay? So at non-standard conditions, the spontaneity, which means thermodynamically favorability of that reaction is going to change, which means that this is another way of saying E cell, the driving force of the reaction, which is also called the does anybody know what EMF stands for? The electromotive force. We're talking about movement, so it's like the electrons moving, so we say motive. Electromotive force. So the driving force of the reaction, the EMF, or the E cell all mean the same exact thing. I know we got like three names for everything in chemistry. But if you change the concentrations or change the conditions, the EMF will change, the electromotive force will change. And we do always start off by talking everything with reference to the forward direction. So this equation that's here in black is not the equation we will use, but it's relating what we're changing to what we already know. The next slide has the one we're going to use. So what we're showing is that the spontaneity or the thermodynamically favorable value changes. So this is the standard one. How do I know? It's got the knot. This is the non-standard one because there's no knot, right? So that's why I try to be very clear when I'm writing knots when I'm not. And then the temperature is going to be coming into play. Q is what? The reaction quotient, which is calculated how? Same as K, so whatever the product concentrations are initially, the I for initial, over reactant concentrations initial. So concentrations come into play. So that's what you guys said. Those non-standard conditions could then affect the spontaneity of the reaction. So how would I end up taking my negative delta G, which is our galvanic cell, and what would happen if I had a large variable in the back? What would that do to my delta G value? Make it what? So since we talk about, like we say it's more positive, but we talk about delta G as a negative value most of the time, to show the spontaneity. So is it going to make it less or more spontaneous? So less spontaneous or thermodynamically variable. Good. And then those conditions that would cause this large variable in the backside would be these two things. A hot battery, meaning a high temperature. So we've all had that we felt our cell phones get warm, right? It happens. And then that's going to like pretty much destroy the battery life because it's like working too hard and it's putting out more energy than it needs to. Or a high concentration of products, because products are on the top of the numerator for Q calculation, which would then impact the value of ln of Q. And then vice versa, the new delta G for a situation where you have your negative delta G and you subtract a large negative number. What would that do to delta G? More favorable, right. And those conditions would be, well, you could say cold, but it's not going to be negative. It's going to decrease the value. So a high number of reactants, though, will stop the forward progress because our reactant concentration being in the denominator will make this value kind of inverted, which would then make that a negative overall term, which is why we get a negative number we've subtracted. Now, the math side of this, some people are going to latch onto that makes a lot of sense. Others of us are going to think about it as a reaction. So I have a reaction, A plus B yields C plus D. As I make this reaction occur and occur and occur and occur, I'm making lots of energy. So my E cell value is positive. How would I make this more positive? Add reactants. Okay, so adding reactants would make it more positive. And what would that do to delta G? Make it more negative, right? More negative delta G. Isn't that what you just said here? It's just Le Chatelier's principle. You increase stuff on the reactant side, it pushes the reaction forward faster, and it's going to make that eventually come to equilibrium again, but we have more energy being produced in a certain amount of time. How would, according to the same setup, A plus B equilibrates to C plus D, how would you take this E cell value and make it smaller? Add products. Products are going to say, whoa, I've got a lot of products here. Stop pushing forward electrons. Like I can't handle the consumption of the products right now. So just going to slow this process down, which is a shift right. And slowing it down makes a lower and lower and lower amount of volts. So it's all Le Chatelier's principle related, but that's the mathematical reasoning behind it. So the Nernst equation, which is this right here, this is the simplified version of it, does relate Le Chatelier's principle to production of electrons, or E cell in our case. Notice there's a knot on one and not a knot on the other, which is why we're talking about conditions that have been changed from standard. Can I move from this? Okay. At 10 minutes, here we go. So, there is a mathematical way to derive the Nernst equation from this equation all the way down to this equation. You don't need to write that down. It's just taking delta G, subbing in delta G, its equivalent, which is negative NFE, right? I'm just subbing it in here and here. That's all I did. And then to get down to the fact where I need to like kind of take some of these variables and collect them together, because I've got E and N and N and F and F, what I need to do is just divide everything by NF, or yeah, NF. In F. So I've basically taken this equation, I'm just deriving it down to one that is really simplified, which this is almost simplified. This is one you'll sometimes see me use, but still it has a lot of variables that I could kind of take constants and just dumb them down to one constant, because R is a constant, right? And F is a constant, right? So two constants, you can pull two numbers into one number. Yes? That's all I've done here. The only weird thing about it is the way they publish it, whenever they publish the Nernst equation without all the constants, they change the ln to log. There's a relationship between natural log and log, but they changed it to log. So I highlighted that to make sure you're clear. I'm not in ln anymore. So this is E cell, no naught, is equal to E naught minus 0.0592 over N, which is what's in, moles of electrons, good, transferred, and then times log of Q, which is our equilibrium constant setup. So, yes, that's what we need to know. if you ever want to calculate it with this one, feel free to. The R constant is what again? Joules per mole. Okay. Temperature would be whatever the temperature given to us would be. If it was a standard temperature still, it would be 25 degrees C plus 298. I'm sorry, 273. I'm calling it 298 already. Now, if the temperature changed, you would then vary that. But in the case where we just have a concentration changing, then I would only use this equation. Because if the temperature stays 25 degrees Celsius, I would simplify and use this equation. If the temperature is changing, I would consider using that one because that's where temperature can then be modified. Are we clear that these are the same equations? It's just one's in log, one's in natural log. One has an uncondensed form of constants. This one has a condensed form of constants. Okie dokie. This is called the what equation? Nernst equation. Okay. So alongside of, as we change conditions, we start to talk about how batteries can die. So a dead battery will mean that no voltage is being transferred, and there's a reason behind that. It's because the battery has met its stable place, and the stable place where there's no more flow of electrons or there's no more changing in conditions will be equilibrium. So we should know now that at equilibrium, E cell is 0, so there's no voltage being produced. Q is equal to K, which, duh, we already knew that at equilibrium, because there's no more changing concentrations, and it's stable. So if you have a dead battery, and you wanted to know initially, before the whole battery died, what was the voltage it could produce at standard conditions, you could then, all you would do is plug in 0 where you would have E cell, right there, and you would rearrange this to solve for just the E naught cell by itself, which is E naught cell minus RT over NF times ln of Q, which is the same thing as this. I just subbed the entire equation. And then solve for E naught cell, which would be the standard voltage. And that would be only if you wanted to know what was the previous voltage before the battery died at standard conditions. Because you can always charge a battery back up with another galvanic cell and get it to charge. But regardless, we're going to use the Nernst equation for most of our calculations. Okay, we got this. Ready? I think I have 2 more slides. I'm going to try in 5 minutes. I have goals. Okay. So we have this cell again. This is the same zinc copper cell. And we know the voltage, and that's what we calculated we saw previously from the reduction potential differences. You guys tell me, and I'm going to phrase it so you understand how to phrase this correctly. What would happen to the what would happen to the voltage if the copper 2 ion is increased? Okay, everybody says shift. Okay, we're going to shift right, and that's because you take your copper 2 ion, you're increasing its concentration. Okay, as it shifts right, continue to tell me more about the electrochemistry. More electrons are popping off of that zinc, right? Because the copper needs the zinc to continue to make copper solid. So the electromotive force, E cell, will increase due to a greater driving force of reaction. You have to specify, since we're talking about the forward direction, we're forcing electrons to be delivered, which would then help us with our E cell value. So shift right, the electromotive force will increase due to a greater driving force in the forward direction. Now, it's not going to drastically change E cell. If E cell is 1.1 volts, it might go up to like 1.2 volts. It's not going to like make a 9-volt battery all of a sudden. So it's probably going to go up some, but you could estimate that and then actually calculate it as well. This is the qualitative side of reasoning, and we're going to do a quantitative. So continue and try to phrase it in the same fashion. What would happen if their zinc ion increased? shift left, and the electromotive force will decrease due to a greater driving force in the reverse direction, or a lesser driving force in the forward direction. You can phrase it very similarly. And then what would be an approximate we could call out for voltage? 1 volt, whatever less is, right? Not 0, it's not the equilibrium, but it would then cause this change. So essentially, you're telling me that changing concentrations will change E cell, which is what we just said with the Nernst equation. We said that as you change these concentrations or conditions, the E naught cell is no longer equal to what we thought it was, or sorry, the E cell is no longer equal to E naught. We've then changed to either increased or decreased. Can I move on? Phrasing here is just going to help you, like, not contradict yourself when you're trying to explain it. Okay. Okay. Previous system. Write down this equation for yourself. So we're going to set up a BDA table. Zinc plus copper 2 equilibrates to zinc 2 and copper. Okay? Determine the E cell. Notice there's no naught, so immediately you know you have to use what? The Nernst equation. For the previous system, after 99.9% of the battery is discharged, meaning the reactants have reacted 99.9%. So assuming that our standard conditions initially apply. So in your BDA, what's your before? Where's 1 molar going? The copper 2 plus and the zinc. This is a galvanic cell. You have two little, anode and cathode chamber. Inside that you have a liquid, which is your aqueous solution. Both of them start off. Does anybody care about zinc solid? No. Does anybody care about copper solid? No. Do not put anything there. It's useless. All right. So during the reaction, 99.9% of the copper is eliminated. It's gone. So how much of this am I subtracting? 0.999 molar. That is what 99.9% of 1 is. As I subtract it from this side in a 1-to-1 ratio, you added that same amount to the product side because of that 1-to-1 ratio. So at the end, when our battery is almost dead, how much copper 2 do I have? 0.001 molar. And how much zinc do I have? So here we go, guys. Here's a new scenario. You've severely decreased the copper. You've really heavily increased the zinc. Is the voltage going to go up or down? The voltage will go down because it's going to essentially shift. It's going to shift left because it wants to go back to equilibrium. It wants to make more copper and make less zinc. So the voltage is going to go way down. So the way we calculate that, though, that's our prediction, is E cell is equal to E naught cell minus 0.0592 over N log of Q. Okay, so there's our equation. I already know one of these. I know this one, 1.1 volts. That's what we've done the same equation 3 times. That is the original standard voltage. N is what for this equation? 2 moles of electrons. And that's because of the equivalent 2 moles of loss, 2 moles gained. And what's Q set up? What's Q set up? No, give me this.
1 over.
No, zinc 2 over copper 2 to the first power. Okay, we'll finish some of these up tomorrow. I want you to attempt. Here's the only thing I want you to attempt right now. Attempt the Nernst equation numbers 1 through 5. Offsets in your packet. Okay. It looks like. Starts with a question like this. Okay. 1 through 5. That's it. Thank you so much for the attention.